uh, I would frequently say, do you want to dismiss early? But then we'd go right up to the buzzer. But today, hopefully, we'll dismiss early. All right. Now, I want to go over the week ahead just in encapsulated form with you, just so you realize what's ahead. And then we're going to talk about supernovas. This is Supernova Day. We're going to be talking about core collapse supernova. But before we do that, I have a couple items of one item of housekeeping that is driving me bonanza. Whose iClicker is this? A6633DF. See, now everybody's checking. Okay, so this is your iClicker question of today. All right? Go ahead and start an iClicker question. Multiple choice. Good, go ahead and start it. Okay, multiple choice. A, it's me. B, no, not me. A, it's me. B, no, not me. Dude, there's two of you that voted for... Come on, this is serious. God bless you. We're trying to figure... Whoever this clicker is, there's four... All right, you guys are... All right, whoever's clicker this is, you ain't going to get any points. You're going to have 0 out of 45 if you don't identify yourself. Because I'm getting clicks, and I don't know whose it is. All right? This is a serious question. But if you guys want to screw around, it's fine. Go ahead. Go ahead and stop it. Yeah? It's yours? All right, see me after class, after lecture. All right. I'm trying to help you guys with grades. All right, now, here's another screen. Let's talk about the week ahead. Now, we're doing core collapse supernova today, of course. There's a diagram over here on the right of a simulation. It looks kind of like one of those MRIs you take of somebody's brain. Like a CAT scan or something. But that's actually a simulated supernova detonation from the Oak Ridge boys. Next Tuesday, and Thursday, we're going to talk about black holes. Okay? Curvature of space-time and black holes. And I promised that I would do that at the beginning of the semester. I promised I would do it. And we're kind of crushing through a lot of stuff, but we're going to do that next Tuesday and Thursday next week. Also on Thursday, the last 20 minutes of lecture, we'll have a mini review using iClickers. And traditionally, I do that in the last lecture. And I'll give you a handout, with 15, 20 questions, multiple choice and stuff. Just as a mini review, and you could do it with your class, with your neighbors. You can, in class here, just like a little mini study session, and it works pretty good. And I converted it into a few bonus points. Now it's going to be 15 or 20 questions, but you're not going to get 15 or 20 bonus points. But I might convert it to 3 or 4 bonus points. Okay. And this is a way of giving you some bonus point opportunity, even if you're never able to go to the observatory. And I know some of you have. You work every night. But this, if you come to class, you'll be able to get it. Also, I traditionally give a mega review homework in web courses on that last weekend. So next Thursday, you'll have a mega review, and I'll convert that one, and that'll be 15 or 20 questions of some kind. And I'll convert that into 3 or 4 bonus points. And that'll help you get ready for the final. And in this class, the final exam is on December 7th. Make sure that you double check your syllabus. And also to reinforce, it's at 7 a.m. So don't get here at 9. And hey, you guys, my rule is always this, and many instructors, the rule is if you get here after the first person has finished and left, you can't take the exam. Now, I don't know if I've done it in this class or the afternoon class, but last exam 4, I had a student come in really late, and I said, no, man, you can't take it. Somebody's already, matter of fact, a bunch of people had already turned in their exams. So if you get here at 9, there will be people that are finished a long time. You won't be able to take it. So get your, you know what, in here at 7, and I'll be here at 6:45. Hopefully I'll be able to get in, and then we'll take the test, and so that'll work out good. Now, last thing I want to remind you of next week, we've got a lot of stuff happening. A lot of bonus activity happening. Observatory session, hopefully next Thursday. 10 bonus points. If it's legible, somebody turned in one. I don't know if it's in this section or the other section. It's completely illegible. It was just written in a, looks like a highlighter, and it's unacceptable. I mean, messy handwriting is one thing, but if it's just like a highlighter, you can't even see what they're writing. It's, you know. So anyways, you have to, and as before, let me reinforce, if the weather does cooperate, and if you go, turn in your observation sheet at the observatory. Do not bring it to me, because then you won't get bonus points. You only get bonus points if you turn it in at the observatory. All right, and many of you have done that. By the way, yesterday I entered grades for a bunch of students for the lunar observation session, October 29th or whatever it was. Okay, raise your hand if you noticed that in your grades. Good. And so you go and see some of the 10 points, and I've got a slot ready, a line on your grades page set up for the, I think it was November 1st at the observatory, and that's an even bigger stack. It took me like 30 minutes just to alphabetize it. So now that it's alphabetized, I can start entering those grades, and I'll probably be doing that tomorrow. All right, so we got bonus points in the books. And by the way, now that you have best 2 out of 3 midterms squared away, you can really get a good idea of what your grade is going into the final. And you can figure out your homework, as I've shown you before in lecture. You can figure out your clicking. And basically, if you have 33 points or more, you have to, you have 45 out of 45. Right? Or no, if you're above 33. So if you have 34 or more, you have 45 out of 45. Otherwise, you have to do that proportion. So you can start doing, and I did that yesterday in office hours, last Friday in office hours. By the way, I'm going to have mega office hours next week as well. Go ahead and make a note of it. I should put it in the slide, but I haven't. Make a note. Monday, 9:30 to 11. Let's make it 9:30 to noon, Monday. All right. And it will be drop-in, but it will be in my main office, PS 156, not the big office hours room 158, which is right on the other side of the elevator. So it'll be in my office, 9:30 to noon, Monday, and next Friday, 9:30 to noon, in my office, PS 156, Physical Sciences Building. And then Wednesday we'll have regular office hours next week. And so if you want to double check with me about clickers or any other the price of tomatoes in China, anything under the sun, But it's going to be on Monday and Wednesday. It'll be in my office, so you'll have to come in one at a time for privacy and stuff like that. Because I can't talk with your grades, when anybody else is around. Otherwise, I get big trouble. Okay, so, all right. Let's talk about exotic fusion reactions and the trouble with iron. These are two concepts, basically, that lead to core collapse, supernova detonations. Now, let's start with the periodic table of the elements and just review some of the things. It might be good for you to take a look at the periodic table and kind of root around in it a little bit. Now, we know that the most abundant elements in the universe are hydrogen and helium. Now, that's on a cosmological scale. Everywhere that we look, the proportions are roughly 3-to-1, hydrogen and helium, and everything else is, about 1% or so, depending on who you ask. In the crust of the Earth, the most abundant elements are silicon, which is about 28%, oxygen, which is 46% by weight, and aluminum, which is about 8% of the Earth's crust. So what is that, 74? That's like 82%, those three elements, in the Earth's crust. Now, if you go into the Earth's atmosphere, you have different elements, of course, because it's a gas. If you go down into the core, you go into the mantle of the Earth. But in the Earth's crust, this is about what we got. The Earth's core is iron and nickel and stuff like that, right? But in the Earth's crust, yeah. So that's an example of the distribution of elements that are cooked up in the inside of a star. Now, we know that, as I mentioned last time, Sydney, that inside a giant star, you've changed over to helium fusion. And helium fusion it's possible under the right conditions to cook up other exotic or other elements on the periodic table. And we know from simulations and nuclear physics experiments that, and from what we know is happening in our star, that most stars on the main sequence, when they get up to giant, the giant branch, the massive ones are going to be able to manufacture stuff all the way up to iron 56. But iron 56 is the last fusion type reaction that will produce excess energy. Now, what's the equation behind the production of energy in a nuclear fusion reaction? Raise your hand if you remember what the equation is. It's one of the famous ones. What is it? You just mouthed something, yeah. Right, E equals mc squared. All right? And the whole idea is that before the fusion reaction, you have a little bit more mass than after. So the stuff coming after the fusion reaction is just a little bit lighter, a little bit less heavy, and that missing mass goes into E equals mc squared. All right? And theoretically, iron is the last element that you can fuse, you can get as a fusion product, and it's lighter than the stuff that goes into it. So you can fuse you can fuse iron, but it won't come, its fusion product will not be lighter. And you can split the atom. Our uranium reaction, our nuclear reactors of today, they function on uranium and plutonium, and our atomic weapons, uranium and plutonium. And those function by splitting the nucleus, fission. And you can split the iron nucleus, but you don't get something lighter as a result, and so there's no missing mass to go into equals mc squared. Now, we're in chapter 23.2, Evolution of Massive Stars and Explosive Finish. This is figure 1, and it shows you that eventually a supergiant star, in other words, a really massive one, is going to have layers of fusion reactions, exotic fusion reactions, some of them long-lived, like hydrogen into helium is going to cook for billions of years. But now silicon into iron, that fusion reaction is going to be very rapid. But it's a fusion reaction that we think is happening inside stars. Okay, and so go ahead and make a note. Figure 1 in chapter 23.2 shows you the different layers that this is kind of what we think. We haven't been able to probe any massive stars, but we think this is what's happening. Now, let's talk about fusion changes under pressure. Now, this diagram is something called the CNO, the carbon, nitrogen, oxygen cycle. And it is a fusion reaction that we see in bigger stars. And it's probably occasionally taking place in the sun, but probably not that often. But in bigger stars, this is the big one. And you still have 4 protons that go in, and you still get 1 helium-4 nucleus as output, but it cooks in the presence of carbon, nitrogen, and oxygen nuclei. And those are heavier, much heavier than helium. All right, so oxygen 16, carbon 12, nitrogen 15. You can see the different isotopes. Here's nitrogen 14 down at about 5 o'clock. Carbon 13 is up there. Nitrogen 13 is up there at about 1 o'clock. And this particular cycle doesn't produce carbon, nitrogen, and oxygen, but it does happen inside of a heavier star, and that's what we're talking about. With a supernova detonation, type 2, a core collapse, it's in a heavier star. Now, after the helium, and this is a pull quote from chapter 23.2, after the helium in its core is exhausted, the evolution of a massive star takes a significantly different course from that of low-mass stars. Now, the sun is a low-mass star. It's going to end up as a white dwarf. And a white dwarf can go into a supernova detonation. That's type 1a. And we'll talk about that in a second. But the bigger stars, you have exotic reactions that we've already talked about. In a massive star, here's another pull quote, the weight of the outer layers is sufficient to force the carbon core to contract until it becomes hot enough to fuse carbon into oxygen, neon, and magnesium. And that's how you start getting these layers. When the layer underneath gets hot enough, you'll start cooking off, like in this case, oxygen, neon, and magnesium. All the oxygen that you breathe, most of it, we think, is produced in that way. In stars that blew up, like that red giant star that we discovered in the McKeegan article on the Stardust spacecraft, and that big, well, I shouldn't say big, but in that cool-looking bullet hole, that's pre-solar grain from that red giant star. Probably a lot of oxygen getting cooked up in that. Matter of fact, that one was pretty hot in Delta 18 oxygen, as I recall. So yeah, your neon, all the neon that we see in neon, like, I don't know if I don't think those are neon. Those are just red glass. But if you've seen neon lights and stuff, that's cooked up inside the core of a star in these layers. Magnesium, very light alloy, very light metal. can be alloyed with steel or with iron and stuff and make light alloys of steel. So now another pull quote. This cycle of contraction, heating, and ignition of a nuclear fuel, of another nuclear fuel, repeats itself several more times until, and so make a side note to yourself, until you get to iron 26. That's where, everything stops. Because you can't, the fusion reaction has to produce heat. It can't be a reaction that absorbs more heat than it produces. We can do those kind of reactions, but you can't sustain a self-gravitating star against gravity without outward thermal pressure. Okay, so your nuclear reactions have got to have a net output of heat instead of a net input of heat. Okay, when you, for instance, when you make ice cubes, you're extracting heat from the water in your refrigerator, using, the refrigeration coils and stuff, the compressor and all that. The refrigeration unit extracts heat from the liquid water enough so that it freezes. And then after that, it'll maybe decrease the, below, a little bit below 32 Fahrenheit. Now, this particular image here, go ahead and make a note. This is Cassiopeia A, Cass A, C-A-S-S-A, famous supernova remnant. And this one is actually a false color X-ray image. And everything that's blue in this reveals an isotope, titanium-44. It's an X-ray wavelength from the titanium-44 isotope. It's just kind of cool. So that's what we're talking about. Now let's look at some of these exotic reactions. Okay, these are what you call helium capture reactions. And the first one is, let me get my cursor here, carbon-12 absorbing helium-4 nucleus. And inside of a star like the sun, there's more and more helium-4 nuclei are building up, so they're going to be around to get socked into the occasional carbon-12. And when it does, the output is an oxygen-16. That's what we have so much of in SMOW. And some heat. So these little rays coming out here from the reaction indicate heat. All right? Or energy. Now, that oxygen-16, if it absorbs or fuses with the helium-4 nucleus, all right, there's some neon. You skip two columns and 4 mass units, and you get neon 20. And then if that neon 20 fuses with a helium-4 nucleus, bing, you get magnesium 24. So look at these numbers. Carbon-12, oxygen-16, neon 20, and magnesium 24. The mass number, 12, 16, 20, and 24, increases by 4 because you fused with 4 nucleons in the helium nucleus. The chemical number, which is not displayed here, carbon at 6, oxygen 8, neon is 10. That's on the far right of the periodic table. And then magnesium is all the way back on the other side in element number 12. Now, so go ahead and make a note, helium-4 capture. All right? It's a kind of an exotic fusion reaction. And you'll get heat output from these babies. All right? Now, here's some more exotic ones. All right? Now, these ones are not helium-4 capture. Look at this first one. This is a carbon-12 and an oxygen-16. And if it's hot enough, they'll fuse. And what do you get? Silicon-28. Silicon that we have so much of in the Earth's crust. All right. And you'll get output energy from that. All right. Because the silicon-28 is just a smidgen lighter than the oxygen 16 and the carbon 12 that went in. They fused, and a little bit of the missing mass goes into energy. All right, that's these little sparkly things here. All right, now, oxygen 16, two of those babies. What if they fuse together? Yeah, in a big enough star, you'll get a layer of oxygen fusion like that. And what do you get? Sulfur, sulfur 31. And you get a neutron. You get a free neutron. This one spits out a neutron. And this little gray job over there. All right? And in these diagrams, the protons are red and the neutrons are neutral color gray. Now, what happens if you have, all right, you got a couple silicons over here. What if these 28 SIs, 28 silicon, 14 protons, 14 neutrons, very nice. What if you have two of those babies fuse? Nice. That's when you get iron 26 or iron 56. All right, 26 protons, 30 neutrons. But now you got trouble because this is the most tightly bound nucleus. Go ahead and make a note. Iron 56 is the most tightly bound nucleus. All right? And for that reason, it's the lightest, neutron for neutron, proton for proton. This is the lightest nucleus. So when you fuse it or when you split it, you're not getting any bonus energy out. You're not getting any good E equals MC leftover mass converted into energy. Not with iron 56. So this is where we think in a self-gravitating system, this is where fusion stops. All right, now that's a problem. Once the core turns into iron, you're not getting any heat output. All right? And so that means everything above the iron core is going to start cooling off, and it's going to start collapsing against gravity because there's no outward heat pressure to keep gravity at bay. All right? So let's take a look at this in detail, the trouble with iron. Now, this is a really nice website, webelements.com. It's got every element. You can click on it, and it'll give you a little blurb about it. It's abundance in the crust of the earth. It's abundance in water. It's abundance in the atmosphere if it's a gas, stuff like that. So it's pretty cool. So if you this is what I was alluding to. If you compute the weight per nucleon, in other words, a nucleon being the generic term for either a proton or a neutron, an item in the nucleus, a nucleon, iron is the lowest. All right. And so for that reason, now let me just get you some. We're going to compare these two. So now let's look at these numbers over here. All right, 26.982. That's the atomic mass for aluminum. 55.845. That's the atomic mass for iron. But let's give it a little bit more precision. If you look it up, these are the atomic mass numbers. Go ahead and write down all the digits. Aluminum, 13 protons in the nucleus, and about 14 neutrons. Iron, 26 protons in the nucleus, and about 30 neutrons. All right, so that's iron 56. And here's the mass of aluminum 27. All right, now what we're going to do is divide each of those numbers by 27 for aluminum 27, and we're going to divide the other number by 56, and that'll give us the mass in atomic mass units per nucleon. All right, so for aluminum, it works out to 0 point, and write all those digits, 0.999316244. And we're carrying all, because they've measured these things really carefully. That's a pretty nice measurement. And for iron 56, nucleon per nucleon, proton for proton. And notice that these two numbers are slightly different. Look out to 4 decimal points. For aluminum, it's 0.9993. For iron, iron 56, it's 0.9988. So that's slightly lower. That means that you're not going to get a lighter nucleus. And another way to say it is you're not going to get any good E equals MC missing mass. And if you don't get that, you don't get any heat output. It's not going to cause any commotion. It's going to absorb energy. It's not going to produce excess energy from E equals MC missing mass. All right, so that's the trouble with iron. Now, here's a pull quote. So make sure that you have number 5, no more E equals MC squared output from either fusion or fission. You know, and really what I should do is put something a little bit heavier, you know, a little bit further out on the periodic table. I should make this into a triple display. But aluminum and iron are pretty good. Aluminum 27 and iron 56. And here's another pull quote from chapter 23.2. Of all the nuclei known, iron is the most tightly bound and thus the most stable. In other words, you're not going to get any good fusion reactions from it. I mean, you could fuse hydrogen, you can fuse you can fuse 2 irons together. You can fuse an oxygen and an iron, but it's going to take energy away from you. You're not going to get any energy out. There's no excess energy, no output energy. There's no missing mass. You've got to add energy to fuse it. All right? And so the result of that is the supernova process. Now, this is a supernova. This is called the Crab. We now call this the Crab Nebula. And this was a supernova back in the year 1054 AD. And there weren't any active astronomers in Europe, like in England or Germany or anything like that. You know, Kepler and Tycho Brahe, this is about 500 years before those cats. But the Chinese observed it. And people saw it. People all over the place saw it. Because it was a supernova that was, they called it a guest star. It was bright enough to see during the day. This is what it looks like now. Now, the 2 different types of supernova. A type 1a. A white dwarf star becomes unstable if it accumulates matter from a nearby star. And we know that there's many, many binary stars. Most stars in the galaxy are in binary pairs. So if one of them becomes a white dwarf, and if it's close enough to another star, it can start, let's say the other star has is becoming a red giant. It starts puffing off its outer layers, and a lot of that's going to accumulate on the surface of its companion, the white dwarf. All right, now, once that gets above 1.4 solar masses, you're going to get a supernova detonation. We think it forms a thermonuclear detonation on the surface of the white dwarf. And it's catastrophic. They're very bright, and we can see them, most of the way across the visible universe, if we're looking at the right time and the right direction. Now there's another type, type 2, also subtypes 1b and 1c, which are leftovers from the old classification system. And these are called core collapse, large mass iron core, core collapse. And these are the ones that we've been talking about with the exotic nuclear reactions. And what happens afterwards is the iron core will collapse, because remember, it's not producing any heat, so gravitation will, and everything above it will start, so the iron core will collapse, like in the space of like, a few seconds, if that. And then because of that, everything else above it, all the silicon layers, the magnesium, the oxygen layers, and all the way out to the hydrogen layers, they'll start collapsing inward too. All right? And what happens is they form a bounce. They bounce off the iron core. The iron core forms a ball of neutrons that will not compress any further unless it's really big, and if it's really big, you get a black hole. So a type 2 supernova core collapse is where, this is the astrophysical process that we think we're fairly confident that black holes like Cygnus X1 are a black hole that formed in this way. In other words, it started out as a really massive star, went into giant status, formed the layers, eventually formed a core of iron. The core collapsed. The supernova detonated outward. All the outer layers bounced. This big shock wave drove it out into the universe and left behind a black hole. And if it's not too big, it'll leave behind a neutron star, which is another kind of exotic object. Now, type 2 supernova. Let's look at these babies. All right, here's an image of a supernova remnant, we think. Right now, this is a famous one. Go ahead and write this down in your notes. Supernova 1987A. This is one that we started observing in 1987. Where, there's probably guys that are still looking at it. Let me get my cursor here. Come on, cursor. Here we go. All right. Now, I want you to look at this. See, it's changing. See that? That's the outgoing shock wave from the core collapse. The core collapses and it bounces, and then the bounce goes outward, and this is several light years across. Diameter is about, I don't know, I think of 1.3 light years, something like that. All right, now let's take a look at that again. All right, look at it. Here we go, 1994, 96, 97, 98, 99, 2000, 2001. Whoa, 2003, it's blazing. What is that? We don't know. We're trying to figure it out. There's 2009. That's when they finished this little movie. Here's what it looks like in X-rays. Over on the right side, that's a false color X-ray image. And the Hubble Space Telescope image is on the right. And what we think is that everything above iron on the periodic table, so gold, uranium, everything else above iron on the periodic table, is manufactured in these shock waves. Extremely exotic nuclear reactions. All right? And then, of course, it's in this big detonation wave. And so a few million years from now, all this stuff will start cooling down. It'll start swirling around with other stars. And, then it'll form planets and stars. And that's where you're looking at gold formation. That's your periodic table factory right there. All right, for another star and another planet, X number of million years from now. But our planet formed. Every item that you have that's got gold in it, everything that you have that's got silver in it, Everything above the periodic table was cooked up in something like that. All right, now here's some specs. Distance, 168,000 light years away. Its location, the Large Magellanic Cloud, LMC. And that's a dwarf galaxy that's kind of orbiting with the Andromeda. You know, the Milky Way and the Andromeda Galaxy are two big spiral galaxies. And then the Large Magellanic Cloud is kind of a dwarf galaxy. And then there's another one called the Little LMC, or excuse me, the SMC, the Small Magellanic Cloud. That's a little, it's discovered by Magellan when he was going across the Pacific. And we're all kind of gravitationally interacting. So we picked it up there. Something called a neutrino burst. The neutrino is a small neutral particle produced in nuclear reactions. In nuclear reactors, in the core of the sun, we can see them streaming out of the SUN. And by looking at those neutrinos, we can figure out some of the conditions in the core of the sun. They have a neutrino detector over in Japan called Kamiokanda, and they observed a neutrino burst, and they observed this supernova. You know, they looked at their records, and they said, yeah, that was SN 1987A. And this thing is it's basically a big ultra pure water tank of ultra pure water, about 3,300 feet underground in the mountains of Japan. And it's shielded from everything else except neutrinos, because neutrinos are neutral particles that just blaze through everything. They'll go through the Earth. They're going through you right now. It's just like, you know, they're very small. They pack a lot of momentum. Well, they pack a little bit of momentum, but there's zillions of them, so they can actually form shock waves around a supernova explosion. The shock wave, here's another picture of a shock wave. The shock wave is about 100,000 miles per hour, we think, for SN 1987A. We think that it was a blue supergiant originally, not a red one. And the ring that we saw in the Hubble picture is about 1.32 light years across as of about 2009. Right. So it's kind of curious, you know, about these supernova detonations. It's kind of cool. Now, the neutron star, the end state of all these supernovas is either a white dwarf or a neutron star or a black hole. Now let's compare a neutron star. That's basically the leftovers of the iron core collapse. All the protons get converted into neutrons. They eject a zillion neutrinos and that's it. So here's Earth compared to a white dwarf. And a neutron star in this image is down here in the bottom middle down here. It's a little speck. All right, so let me put the neutron star into perspective. Basically, you're talking something about the size of a city. All right. Now we can see a neutron star. They produce a lot of them produce a lot of radio waves, what we call a pulsar. Because a neutron star also has very strong magnetic fields. If the star it came from had a magnetic field, the neutron star will also have a high magnetic field. Right, here's a picture of a neutron star. Maybe 1.5 times the mass of the sun, 12 miles in diameter. So it fit comfortably inside of Orange County. Solid crust, about a mile thick, and we think it's a kind of a neutron liquid conditions on the inside. There's guys that this is what they study, and I'm not a neutron star expert. I know a little bit about them in terms of quantum field theory and stuff, but they're considered exotic objects. But the interesting thing about them is that they form pulsars. And a pulsar is basically a neutron star that is spinning and has a high magnetic field. If the magnetic field axis points toward Earth, we will get a lot of radio waves from that pulsar. If it also is spinning at a high rate, they spin at a very high rate usually because they're so small. That this magnetic axis up here will point towards Earth once every time it spins around. All right, and then it goes around. And so if you're listening from Earth, you'll hear it as a series of beeps. All right? So neutron star, if its magnetic pole points slightly towards the Earth, there's a little bit of angular leeway, so if you're somewhere inside that cone, if Earth is somewhere inside that cone, our star system, then we're going to hear beeps, and we're going to hear them every time it spins. Right now, that's called the lighthouse effect. Go ahead and write that down. Neutron stars, strong magnetic field, magnetic pole pointing roughly towards Earth. Lighthouse effect, we get a beep every revolution of the neutron star. All right. The first pulsar, pulsar, that's what we call them now, because they have a regular beep every time it spins. The first pulsar I think it was 1967. A young lady in England was listening to data or examining data, and they found from a radio telescope. This radio. These big radar dishes that you have for satellite signals. They make even bigger ones to listen to stars and galaxies and stuff in the radio frequencies. And so she was listening to this or studying the data files, and they found a beep. They found a regular pulse. The signal strength went up, signal strength went down. Signal strength went up, signal strength went down. Signal strength went up, signal strength went down. Very quickly, up and down, on a very regular scale. So this grad student, her name is Jocelyn, you could probably look it up, Jocelyn somebody, in England. She's looking at this data, and so you know what they called it? They didn't think it was really true, but they called it LGM. They called it the LGM back in 1967. LGM, capital L, capital G, capital M. You know what that stood for? Little green men. Because they thought facetiously, okay, somebody's signaling us, And you know what? If there really are aliens that are signaling us, it'll probably come through like that as well. So they were, we haven't found any extraterrestrial intelligence, but that's what people were thinking at the time. Now we know that the LGM that they discovered, Jocelyn, I can't remember her last name. I usually mention her by name because it's a famous ripoff in science. Her graduate advisor, her thesis advisor, she's a PhD student, right? She discovers it, figures out what it is, but her research advisor got the Nobel Prize for it. She didn't. So nobody mentions him anymore. We always just mention Jocelyn that discovered it to make her more famous than her loathsome advisor. Anyways, there's a lot of science ripoffs in history, and that's one of them. But anyway, she discovered this, and we've since found zillions of them. They're everywhere. Now that we know what to look for. Now, extraterrestrial intelligence, it probably won't be just a beep. You know, a lighthouse, beep, 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 beep. It'll be Morse code. You know, it'll be like the internet. They'll be sending us a signal. You know, so instead of beep, 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 it'll be $5 off pizza tomorrow night, Sagittarius A, you know, or whatever, or wherever they are, they'll be sending us messages that we could decode. Hopefully. Now, we haven't gotten any yet. And that movie Contact, raise your hand if you've ever seen that. Okay, make a note of it. It's worth looking at. It's kind of hokey because there's like, you know, romance and pretty girls and all that stuff with, you know, Hollywood. There's a lot of Hollywood jazz. But it's based on a real life person named Jill Tarter. Oh, and also, well, I'm not going to spoil it for you, but there's a lot of hokiness in it. But it's based on a real life person and the search for extraterrestrial intelligence. And I've actually talked to the person that it's based on, Jill Tarter. And it's kind of an interesting movie. But it's about, you know, how do you tell you know, an LGM from a real LGM, a real little green man that is actually sending us, you know, discount coupons for his pizza joint or whatever it is he's sending us. So that movie Contact, it's got Jodie Foster in it. And, I mean, if you can get past the, you know, the stuff that makes you gag, there's a lot of cool science in it. It's worth that they didn't screw up too badly, which Hollywood usually does. But speaking of screwing things up badly, here's another topic that they screw up badly: black holes. If a star's DNA is large enough, the core will collapse, but neutrons, something called neutron degeneracy pressure, will only hold up the core at a certain density. If you exceed that density, nothing will hold up the core. It'll collapse into a black hole. All right, so maybe 20 solar masses or more, you're talking probably a black hole for the end state. And that, my wonderful student, is what our topic will be on Tuesday next week. Now, if you have a clicker problem, I want you to come up here right now. We're going to have a special clicker clearance, and especially you in the back. I want to talk to you. You're dismissed. I'll see you guys next week. Have a beautiful, blessed Thanksgiving Day.